Hello students, welcome to Lab 9. Today we're going to start talking about machine learning. Now, this is a pretty exciting concept, but we're not going to quite get into the standard way of doing machine learning yet today. Instead, we're going to build up from scratch. We're going to understand what the fundamental ideas are behind machine learning, what we prioritize when we do machine learning, and how we test whether we've done a good job or a bad job when we fit these models. As such, I've broken up the machine learning segment into two different labs. Today, we're going to get a good understanding of the basics, things like defining the problem. What sorts of problems do we use machine learning for, or are they really particularly well suited for? Then we're going to talk about some of the more ticky-tacky details. Why is it that we split up our data into two sets before we fit a model, and what purpose does that serve? After that, we'll talk a little bit about models. Not a lot. We're only going to use model in the very vaguest of senses. We're not really going to talk too much about linear regression, anything like that. We may touch on that a little bit, but generally speaking, I want you to understand a model as a general set of rules or approaches that we use to make predictions. Then we're going to talk about errors and error metrics, which really help us understand how we're wrong and how much we're wrong. Really, that's the core idea behind prediction. We want to minimize how wrong we are, and certain characteristics of that wrongness are more or less desirable. We don't want to be systematically wrong. We kind of want to be randomly wrong. If you're randomly wrong, that suggests that there's not really that much information left to squeeze out of your data set, and a lot of other properties that we'll briefly cover on. Lastly, we'll talk about normalization. What can you do to your data to improve the quality of your predictions? So, as I mentioned, we're not going to do any of this today in sklearn, which is the library that is far and away the library that almost everybody uses to do machine learning tasks. It is, when you get out into industry, if you've already built machine learning models, that's probably what you've used. If you haven't, that's probably what you will use. There's not really a major competitor to sklearn when it comes to the types of data sets that we're going to cover today, which is tabular data sets. That's really mostly what you'll be covering. So let's go ahead and let's open up a new file. We are, of course, going to start up a Jupyter notebook. We are going to save this under Lab 9. I'm going to call this Lab 9. And then I'm going to import NumPy as NP, import pandas as PD, from plot9, import star. And I'm just going to run that, and I'm going to say, yes, please run it as Python. I also want to read in the diamonds data set. So let's go ahead and do that. Let's take a look at our data. Okie doke, here we go. Now, this is a data set that we're quite familiar with at this point. We know that it contains about 54,000 instances of diamonds, of which we have numerous different variables that we can use. So we know what its carat is, we know what its cut, color, clarity, depth, table, its price, and then these XYZ variables, which seem to be some sort of coordinate variables, but I don't really know anything about diamonds, so if you know what XYZ stands for, let me know. But clearly they've been measured very carefully, and they're meaningful to people who know anything about diamonds, so we'll take it at that. Let's talk about the very first step, which is let's define our problem. Let's say you are interested in knowing what the price of some unknown diamond will be. Someone came up to you, they showed you a random diamond, and you want a good estimate of how much this diamond will sell for, its price, right here. This person who is presenting this diamond to you has, for some reason, taken all of these other measurements. They know what the carat is, they know what the cut, color, clarity, depth, table, and XYZ are of this diamond, and they've asked you to take a good guess at price. How might you do that? Probably a first good guess would be to say, well, I know other diamonds that are roughly this shape or this weight, for example. Other diamonds that are about a quarter of a carat tend to go for about, I don't know, $300-400. So I'm gonna guess 350. You're using the information that you have in your mental model. You're making a relationship between these two variables, and you're taking a guess. Now, last week, we implicitly did this by plotting our data set, right? We did something like this. So we started ggplot. We said, look at your data. On the x-axis, I want carat. And remember, it has to be in quotes. And on the y-axis, I want price. And why don't we go ahead and just make a scatter plot. Keep it theme minimal, like all the cool kids. And let's take a look at that. This is the model that we're making. When we see this scatter plot, we see this kind of very clear exponential type relationship, where as carat goes up, you can kind of imagine a curved line going like this. If someone gave you a quarter carat, someone showed you a diamond that was a quarter carat, you say, probably not that expensive. If someone showed you a 2 carat diamond, you would say, wow, it's probably likely to be a lot more expensive. This is the type of problem that machine learning tools are very good at solving. Each new diamond is basically an independent observation. If I know the carat of some random diamond that got dug up somewhere, I don't really know what the carat of any other diamond is going to be, so they're independent observations. And it is useful for me to have some sort of model that predicts very accurate sale prices for a diamond. If I'm a jeweler, for example, someone brings me raw diamonds, I want to know how much I should pay for them, for example, so that I can still make a profit. Or let's say I'm some sort of like trader, right, on the stock market. I want to know how much to pay for a stock if I predict that it'll go up in the future. So these are the types of problems that machine learning tools are very good at solving. Prediction problems. Not all of the problems we want to solve are prediction problems. For example, basically all of academic research, outside of the machine learning literature, obviously, has to do with assessing the effect of some cause. That's not a prediction problem. You may think of, for example, in the political sphere, what's the effect of having some policy on some outcome? For example, if you increase the cigarette tax, what happens to the rate of smoking? This isn't a prediction problem. This is what we might call an estimation problem. Right? Prediction problems are rampant in industry. I work at a food company, for instance, and it is very, very useful to be able to predict what the price of, for example, commodities are, like pork bellies or soybean or corn or oil. Because if we know that the price of those things is going to go up, if we can predict that with a high degree of accuracy, then we know whether to buy now, whether to buy later. You can make a lot of money doing that. Most of my job is not that impressive. It's more about selling more tater tots to customers or onion rings. But that in itself is a form of prediction too. Predict which types of customers will buy more of the thing that you want to sell. That's a classic problem in industry. So that's part one of the definition, right? We're trying to predict something. And importantly, we want to predict on observations we haven't seen yet. Of course, we could just fit a line here. For instance, we may just want to say, just to fit a line to this data, and let's see what we get. And of course, it won't be a terrific line, but it'll give us some sort of, there we go, right? I don't know why the line goes all the way out there, but that's fine. It is what it is. This line gives us some reasonable way of estimating what the price might be for the diamonds that we have already seen, for the 64,000 diamonds in this data set. Let's go ahead and make this a little easier to see, shall we? If I already know what the carat is, I can just go up to this line and I can say, yeah, guess about this, and you'll be right on average, right? But what's really important is for us to be able to make predictions on observations that we haven't seen yet. It's no use to me to predict what the price of a diamond is that already sold. I already know how much that diamond sold for. What I want to be able to do is to create predictions for diamonds that I haven't seen yet, that someone may bring to me, right? I want to know what the price of commodities will be in the future. I want to know which customers of those who haven't already bought this item are likely to buy this item. Right? So that's kind of a second part of this definition. We're not only making a prediction, but we're making it on observations you haven't seen yet. The third part, or defining the problem, the third thing that kind of sets machine learning apart from other types of prediction, for example, like astrology, for example, is that it uses some type of rule that you define beforehand. Now, I use the word rule here. We may just as well use the word model. Now, don't be intimidated by the word model. Really, all model means is we have some process that we define before we make our prediction that you can then, after the fact, go back and say, yep, that's how you did it. This differs from some ways. For example, think of elections. In the aftermath of an election, in the lead up to an election, you'll hear all sorts of people make all sorts of predictions about, I think such and such candidate is going to win for this reason, for that reason. After the election, how many of those prognosticators do you hear saying, I got it totally wrong? I made a prediction based on these factors, and clearly my model was just incorrect. Basically nobody. What you hear these people say is, actually, looking back at it, it was obvious all along that XYZ candidate was going to win, right? These people are not using a consistent model, right? You need to be able to verify your work, because if you just go backwards and you say, oh yeah, of course it was obvious all along, that's not useful. That's not a way to make a consistent prediction going forward. So, let's talk about a train test split here for a second. Let's take a look at our data again. And remember, the goal for us is to be able to predict what the price of a diamond is going to be that we haven't seen yet. And so let's take a crack at it really quickly and see what that might look like. One way for us to do that might be just to say, just predict the average price every single time. Right? So we might say, naive prediction is, we're going to create a new column, and all I want to do is just take the mean of price. Right? And if I take a look at my data set, there you go. The observation is the same for every single one, right? So use a different model to predict. So this is what we've done, right? All we've done is we've taken the mean of price, we've put it into a new column, and as you'll see, the mean of all of this column right here, the price column, is always going to be the same. Obviously, it's just one number. So what we've done is we've created some sort of model here. I'm going to move some of these down for a second. We'll cover those a little bit later. What we've done is we've created some sort of model. If you show me a diamond that's not among these 54,000, I'm going to say, I bet you that diamond costs roughly $4,000. It won't matter if you bring me a diamond that is 1/4 of a carat or 5 carats. I'm always going to guess 4,000. Intuitively, you may think that that is a bad way to make predictions. Just based on vibes alone. Be like, wow, this guy is stupid. He has no idea what diamonds are worth, right? But what we kind of want to do is we want to move beyond that. While I'm all for vibes, and I think it's totally valid to judge, for example, a visualization based on its vibes, it's less helpful in machine learning. We want to quantify our vibes. So how do we do that? One way to do that, and we'll come back to models, one way to do that is to measure how wrong we are. We want to know what our error is. One way that we can measure our error is just to take the actual price that we saw and take out our prediction. And why don't we go ahead and call this the naive errors. By the way, the word error, whoops, is also, you may hear the word residuals. These are our residuals, and you'll notice that they differ. These are not all exactly the same, right? So for example, you notice that these two are $1 different. These, which sold for a much higher price, for roughly almost $3,000, are, the error is much lower. We still overguessed, but we didn't overguess by quite as much. This is a little bit unintuitive, right? If you overguess, it shows you negative because your residual, what's left between your prediction and your outcome, is about this much, right? You overpredicted it. Alrighty, so this is a way for us to measure at the individual level how wrong we were. This is our error. But this individual level error isn't necessarily useful if we want to understand the behavior of our model overall. So one thing we may need to do is to just figure out some way of summarizing this. So why don't we do that? Why don't we take some errors? That's a hard word to spell. Why don't we just take the average and see what happens? That doesn't seem quite right, does it? It's telling us that basically our error is essentially 0. This basically means 10 times 10 to the negative 13. So it's saying, on average, you're right. And you're really right. You're very, very close. Something has gone wrong here, right? The mean, it seems, is not a useful way of measuring the overall performance of our model, right? So we created our model. All we did was take the average, and then we said, okay, how wrong were we for every individual one? And then I just want you to take an average of that. So let's explore that a little bit. Why are we getting what we get? One way that we can visualize our errors is to build a plot. Right? So we're going to say data. On the x-axis, I want to put our prediction. On the y-axis, I want to put your actual value. And I want to make a scatter plot. The other thing I want to add is a line that goes from 0 and is just a correspondence line. So when the x variable is 1, the y variable will be 1 as well on this line, right? Since we're putting predictions on the x-axis and price on the y-axis, a perfect predictor, which our mean is apparently telling us we're very good at, will mean that all of the dots will fall exactly on the line. I don't think that's happening, so why don't we observe that to see if that's the case. And geom abline takes the argument's intercept, which is 0, and slope, which is 1. Let's take a look. Let's take a look and see what we get. Okay. What happened here? Pretty obviously, our lines are not making a whole lot of sense right now, right? Let's take a look at our predictions and notice that all of our predictions are basically exactly the same. Well, we know that's the case because we just used the overall mean to say that. So this plot is not particularly helpful. But one thing it does show me is that there's no way that our errors are basically 0 when we take the mean. What is probably happening is that a lot of these negative errors are canceling out a lot of the positive errors. For example, let's say I had a list. Let's go ahead and make a NumPy array, just like we did last time, with the values -1, 1, 0. And then let's go ahead and take the mean. That's telling us that the average of this set is 0, which is correct. That is technically correct. Let's assume now that these are all of our predictions, but the actual values for all three of these are 0. You were off by 1 for this, you were off by 1 for this, and you were spot on for this one, right? Really, your error should be something close to 2/3, right? You had 3 possible chances. Of those chances, you were wrong a total of 2 units over 3. So one thing we might do is we might say, okay, what's the absolute value of that? Is the absolute value possible? Alrighty, thanks for your patience there. I had to go remind myself what the function for the absolute value was. So let's take the absolute value of that and then take the mean and see what we get. Now this seems like a much more sensible error metric than we had before. So why don't we go ahead and why don't we apply that to our data? So why don't we take our naive errors and say, I want to take the absolute value. Looks good to me. And then why don't we then take the mean of that? This seems more reasonable. What we have here is a metric called the mean absolute error. As the name implies, it is an error, so the smaller this number, the better. What we're looking for is a type of model that will consistently beat a prediction error of 3031. This is saying in an absolute scale, on average, your error is about $3,000. That's really big. That's really big, right? Now, having seen our data, let's go ahead and comment this real quick. Carat versus price. Having seen our data, we know that there's probably a lot of information in here that we can use to make better predictions. For example, we might say, hey, I bet the better the cut, the better the price. And in fact, why don't we go back and see if that's kind of intuitively true. Let's make our visualization reflect these things and then see if that actually helped. And I'm going to get rid of this Geom Smooth here for a second so we can zoom in on our data set. Yeah, it's possible. I see a lot of these fair, which is the lower quality of diamonds near the bottom. I see a lot of these green ones, which is ideal, near the top. And I don't see any purple ones near the bottom except for this one. I don't really know what's going on with this one. But in general, I see purple closer to the top. I see orange closer to the bottom. Okay, so far we have our data. We know we want to group by the quality of the cut. And we know our outcome variable is going to be price. And now we want to use the transform function, which returns a data set that has the same number of rows as our original data set. And we want to tell it, I want you to do the mean transformation. Let's go ahead and do that and see if that worked. Yep, sure enough, we got different values for different cuts, right? Now, we can do the same thing. Say mean absolute error. This is naive prediction. And we can call this grouped prediction. So why don't we calculate our errors again? So we can say grouped errors, and we're going to do the same thing that we did for our mean. We're going to say data. We're going to take our price, which is our outcome variable, and we're going to subtract our grouped predictions. And I'm going to take this out for a second. I'm going to put it into its own cell. We're going to run this, and we're going to take a look at it. Yep, sure enough, that seems to have worked. So let's do the same thing that we did last time, which is take the absolute value of this data. We're going going to do NP absolute value. Alrighty. So here we have error of the naive model. And here I want to wrap it in print. Cells in an IPy notebook will always display the last thing that you did that prints out to the console. So if I don't wrap this in print, I'm just going to get this line rather than the naive errors line as well. But what I really want is to see what my group errors are. So let's see. Clearly we've improved here, right? So 3031 is the error from our naive model. 2990 is our error from our grouped errors model. And you can imagine ways that we might do get a little bit better. For example, there's clearly a trend. And in fact, why don't we do something? Why don't we plot our group predictions versus our actual price. Now we're starting to get somewhere. Clearly there's some amount of variance. We're not making the same prediction for every single diamond, but it's still not quite satisfying. There's really only 5 categories of diamonds. And really looking at this data set, we haven't even used the variable that is probably most explanatory, which is carat, right? So we'll get back to that in just a second. Generally speaking, though, we've covered what an error metric is and how you calculate it. Right now, we've worked on an error metric that is the easiest for us to understand intuitively. Mean absolute error is an error metric that you could see yourself coming up with. If you asked yourself the question, how can I measure how wrong I was on average? And we've seen that incorporating different variables into your model can make it perform better. In this case, not drastically better, but better, right? Okie doke. There are, of course, other ways, other types of models that we can fit. For example, we may fit linear regression. Now, when we originally fit that geom smooth, that's what it was doing. It fit a line to this data that took in your x-axis as carat and your y-axis as price, and it fit the line, the straight line, that best fits this data. We won't get into what best fit means, except to say that it minimizes that error metric. That line, the error metric we use when we fit that line is not the mean absolute error, but it's something similar called a root mean squared error, which we'll cover in a little bit more depth in the next section. So let's get back to the general problem that we're trying to solve here. Let's delete this for a second. Let's clean this up. You can, of course, in your own time, go through and try and figure out different ways of predicting this. You can incorporate other variables. Feel free to have fun with this, right? See how low you can get this error metric. But let's get back to defining the problem. We want to know what our performance will be on observations that we haven't seen yet. Of course, this poses a problem to us because if we haven't seen an observation yet, then it's obviously not in our data set. So we need some way of mimicking this behavior. We need some way of holding out some number of observations and then not teaching our model on everything, but rather teaching it on some subset and then using what we learned to predict on cases it hasn't seen yet. So this might be a little bit abstract, but let's simplify this for a second. Train, test, split. So let's say I'm just interested in 2 variables right now. I want to look at cut and I want to look at price. That's it, because those are the only 2 variables that we used to create our model up here, right? We just took the group by mean, and that's pretty much it. One thing I want to do is I want to simulate this behavior or simulate this scenario where I don't have access to all of the data that I really want. For observations that I haven't seen, obviously they're not in my data set, so I can't predict on those yet, but I want to hold out some number of observations in my data set. One of the things that we can do to recreate this scenario is just to hold out some rows. And we can do this with the sample function. So we might say sample fraction equals, and let's just hold out 0.1. Here I get about 5,400 rows, right? Which is about 10%, which is exactly what we got. We're going to call this the test set, right? But this is kind of a cumbersome way of creating this test set. For now, let's just forget about it for a second, and let's see what we've got. Great. We have our test set, but we're not going to use our test set to build our model to learn anything from. Instead, we want to use what's left after pulling out this 10%. So one way we might go about holding on to that remaining 90% is just to create another data frame that contains all of the observations that are not in our test data set. So let's take a look at our test data set. And remember how I said in the last lab that the index can turn out to be quite important sometimes? Well, this is one of those cases. So let's take our data set, because we want to start with that full data, and I'm going to say drop. Drop can, as its name implies, drop columns or rows. In this case, we want to drop rows, but we'll get to that in a second. We want to know which rows to drop. Now, this is still our test data set, and we know that we want to drop any rows that have these indices. So I'm going to say drop anything that is in the test index. Now, if I take test index, for example, it'll give you all the numbers that are in there, right? 4027, 4027, right? So here's a list of locations for the rows that we want to drop. And now drop can drop either rows or columns, so we need to tell it to drop rows, which is called axis equals 0. And you'll notice that we don't have 54,000 rows any longer. We have 48,000 rows. So let's go ahead and put that in a data set called train. Let's run that. And if we look at test, and if we look at train, we get basically two complementary data sets. Together, these are our entire data set. And in fact, why don't I make this a little easier by filtering down to test and train. There you go. Right now, we only have the two variables that we're interested in. Now, why don't we go ahead and why don't we copy the code that we used up here, and let's make our group predictions, right? Because we know, for example, that our grouped model performed a little bit better than our global model, and we're going to say make grouped predictions based on train set only. That's it, just based on the train set. So, in fact, in this case, all I really want to see is what the outcome looks like. Because at the end of the day, while it will be useful for me to know what my error is on my train set, what I really want to know is what my error is on my test set, because that's the set that I held out. This is me simulating what it looks like to get new data. So let's say I want to take my train data set. I want to group by cut. I want to take the price, and I want to know what the mean is. And these are my predictions, right? There's only 5 predictions that I can make, and that's about it. And I want to turn these into a data frame. And as I noted, you'll see that price is kind of above here. This is kind of what happens with the shenanigans with the index when you do aggregation methods. So I just want to reset the index, and I'll treat this like a normal data frame, right? So I'm going to call this one predictions. And let's take a look. We have test, we have predictions, And now I need to put these together. Right? So why don't we do one last thing, which is rename the columns on our predictions data set. So I want to call this predicted price instead. We'll say columns are equal to, and here I'm just renaming the columns of my predictions. I want to keep cut because I want it to join on cuts. You guys remember left joins from what we did in R, but I want to rename price grouped price. And if I look at, oh, whoops, I did the wrong one, didn't I? Okay, never mind. I want to change my predictions column to grouped price. Okie doke, there we go. So group price, test is back to how it should be. Awesome. So let's take test and let's merge on our predictions. Let's see what we get. We get our cut, we get the price that was actually paid, and then we get our prediction, right? And why don't we go ahead, so that's outstanding, right? So train test outcome, we're gonna call that. And now we want to do the same thing that we did here, again and again and again. All we want to do is we want to look at what our error is. So we're going to take train test outcome. Test outcome. I know it's a bit of a mouthful, but hopefully you'll bear with me here for a second. Oh, whoops. I did not call it grouped error, did I? I called it grouped price. Whoops, my bad. There we go. And let's take a look at what we got. Train test outcomes. And let's do the last step, which is to take train test outcomes. We're going to look at our grouped errors variable, and we're going to take the mean. 2984. You'll notice that this is a different number than 2990. There's no reason to believe that we got better at predicting, because this number is lower, by using less data. Rather, this error is more the result of random chance, right? If I were to take a different 10% randomly and were to run through this whole process, I'd probably get a different number. And in fact, why don't I just do that? Let's see how that goes. Yep, 2972. And if I do it again, 2976. Some of those numbers are going to be bigger. Some of those numbers are going to be smaller. That's the nature of randomness, right? Some variables, or I'm sorry, some observations end up in our train set some of the time. Some observations end up in our test set some of the time. So let me go ahead and comment this real quick. I'm going to say rename column. So predicted price is preserved in the merge. Merge predictions onto our test set. Calculate individual errors. I'm going to say calculate mean absolute error. I don't think we're going to cover this one today, but that's okay. It's more appropriate for tomorrow. Whoops. Anyway, alrighty. So what have we done today? We've done a couple of things. Let's start back at the top. Imported our packages as normal, loaded our data as we often do. We visualized our data and we noticed some patterns. Next week, we'll make better use of these patterns by fitting different types of models to this data. You can obviously see that there's some sort of curvilinear relationship. We didn't really take advantage of that here, but we will moving forward. Then we created a couple of different types of models. We created a very naive model, and we created a grouped model, which you might still call naive. It's not good at predicting, but it's one way that you might start to predict. Then we looked at how do we calculate our wrongness? How do we know which models are better or which models are worse? And we looked at error metrics. We calculated our individual level errors, and then we kind of aggregated them together here. And now we can say, okay, we have some objective way of measuring which model is better, which one consistently produces better predictions. We can see, for example, that if you include information about cut, which is the second model, then your model tends to predict better. Not much better, but $40 can be a lot if you're selling a lot of diamonds over some amount of time. We also looked at visualizing our errors. This isn't a particularly helpful visualization this time around because we're using a very silly method of making our predictions. Usually you would want something that looks a little bit smoother, but it still kind of shows us how we might interpret our errors. We can see that there's a lot of variance around each of these. These 5 categories don't seem to be that explanatory, so clearly we're missing a lot of data here. Then we talked about simulating that experience of held out data by using a train test split. And so we did that, and then we kind of recreated the process of fitting the model of making our predictions on a train test split data. We renamed those columns just to kind of keep things clean. We made our predictions, and then we merged them onto our data set, and then we measured how wrong we were, right? And we were less wrong than we were before, right? Or roughly as wrong as we were before. All of this, as a final note, you may come to note, is quite cumbersome. Every time I fit a machine learning model, I don't want to have to do this sort of munging from scratch. I don't want to have to make models that are group by aggregations. Although you can use some features that make use of these aggregation features, and you'll learn to do that as you get into industry and spend a lot more time model building. I want a set of tools that can make a lot of this ticky-tacky stuff much easier. I don't want to have to worry about all of this sort of method chaining nonsense. Right? I don't want to have to worry about the index. I don't want to have to worry about taking aggregations and things like that. All of this week is basically set up for next week, which is the set of tools that can help us do that. sklearn is to machine learning what dplyr is to data analysis. It is difficult to imagine doing machine learning without sklearn. Now here, we've done the very, very simplest version of a machine learning model, but hopefully the concepts are starting to come across, right? Hopefully you're starting to look at this and you're starting to say, how would I model this behavior? A continuous versus a continuous variable. Next week, when we do sklearn, we're going to talk about how these models in sklearn are conceptually designed to slot in for one another. There's a lot of different ways that you could have made a prediction. We chose a very simple way, and we can replicate that in sklearn. But for example, we could just as easily use linear regression. We could just as easily use a random forest. We could use any sort of, boosted model like XGBoost or CatBoost or LightGBM or anything like that. So next week, we're going to go a little bit more into that. We're going to talk about what the pipeline looks like, how to look at your model building code as a sort of recipe that recreates a lot of the functionality that we motivated here from the ground up using very simple code. So had a fun time doing this today. Look forward to seeing you next week. Go ahead and get into this notebook and try and practice. See if you can come up with different ways of making predictions on this before you use scikit-learn. I feel like that will probably give you a good sense of what it is we're doing when we drop in different estimators or models in sklearn next week. So keep at it. We're almost through the difficult stuff in this class, so keep up the great work and see you next week.